what you're getting on the left side? So natural log on the left side, you get negative 0.883 equals natural log on the right side, negative 0.452 t sub f, and divide through on both sides. And you get what? Follow? No? Do natural log here, natural log here. This is this. This, they kill each other, and you get that? Is that the part you were hung up on? No, further back?
Like, the resin number so I could put it down.
Okay.
Sorry.
So you're all right?
Yeah.
Okay. What do you get? 1.94? 54, close enough. Is approximately T sub F. So? What? What was T sub F? The time when we found the body. 1.9454 hours. Why is it hours? Because we waited an hour, right? So we were measuring everything in hours. So what would happen at 0? At time of 0 is when the person died, right? It would be 98.6. But here, we're saying that the time when we found it was 1.954 hours from when time was 0, which is when they died. So they've been dead for about 2 hours.
We wasted more time than they'd actually been dead when we found them.
That's right. Took us 2 hours to figure out that they've been dead for 2 hours.
Was that 2 hours including our hour? Or
No.
2 hours.
No. Because what happened was we didn't know what T sub F is, right? We can say roughly it's about 2, all right? Is that close enough? It's about 2 hours.
When we found them,
They had been dead for 2 hours. We didn't know that. We waited 1 more hour and took their temperature. So if you look at it in the big scheme of things, at time equals, if I look at it this way, at t equals 0, they were 98.6, right?
Wouldn't that be like your answer that you got over there? Wouldn't that be for T of F or T sub F plus 1?
Hold on. This is the time they died, right?
Okay. No, because it canceled.
T sub F is when we found them, which we're saying is what? 1.94? Let's just say 2. That's when we found them. Their temperature was what? 83? 1 hour later, we measured it, and it was what? 79 degrees. That's kind of a table of what just happened. This was T sub F. This was T sub F plus 1, right? If this is 2, then an hour later was 3. We didn't know it, but when we took the temperature the second time, that was 3 hours after they died.
So when we found it, it was...
They've been there for 2 hours. So what they can do in the real world is they have, pretty precise instruments. They don't have to wait the full hour perhaps, and there's other methods, that they can look at other parts of things that naturally happen when you die. So does this make sense though? Sorry that I walked out of the room and left you with that, but I wanted you to think about what you had, what you could actually do with the information you had.
And how screwed we were without you.
I guess so. You need more information than you had. Just that one temperature reading wasn't enough. You had to take 2 in order to determine time of death.
Would that be on the final?
So that's why.
So you want that on the final? Hold
No.
on. You want that? Make
No.
sure I put that on the final. By request.
That would be my whole entire final.
Just her final.
Just her final.
Just her final. All the rest of us have easier ones.
Yeah, that one problem is going to account for like 70% of her final.
All right, we move on. We got 35 minutes.
Yes, we just get linear equations.
So look, out of this section, what was that, 6, 8? There's a couple of other models that they have in there. We've talked about exponential growth with, what were we doing? No, we did decay. What did we do on your test?
It was decay.
Half-life, sorry. We did half-life, right? But you could do growth problems. They have like bacterial growth problems in the book. Same concept with a positive K. There's radioactive decay, which we talked a little bit about. Okay, that's in this section. There's Newton's law of cooling, which we just did. There's logistic models that are in this that I'm not covering. And I'm telling you this because I want you to see that in this section there's like 5 or 6 different applications of exponential functions, of which I like to touch on like 2 or 3 of them. I will only test you on those 2 or 3. So in your homework assignment for this section, if you get to a problem, it'll tell you in the beginning of the problem in bold, it'll tell you like bacterial growth, or it'll tell you radioactive decay. I think anything that has growth or decay are fair game questions. There are some problems that say Newton's law of cooling. Those are fair game. But if it talks about logistic models, you don't have to worry about it, all right? My test will stick to radioactive decay, half-life stuff, some bacterial growth, and Newton's law of cooling. That's the spectrum of what I will give you on a test. All right, we're going to move to a different chapter. Chapter 12. Systems of equations.
There you go.
And inequalities.
That's what they always say.
You did what?
How easy would you say?
Students do pretty good with this. As you'll see, the only real issue you run into with this is that there's a method, there's a process that you follow, and there's a lot of room for error, like in terms of your calculations, arithmetic calculations. But conceptually, I think it's pretty straightforward. So,
Like logs.
not like seeing logs for the first time, yeah. All right, so we're going to start in 12.1, and this is called Systems of Linear Equations and I'm going to add something to this title that the book doesn't have. 2 equations, two variables. Oh, you know what? They do 3. Sorry. They do 3 in this section. I thought it was 12.2 that they did the 3. Hold on. Let me double check. They do 3 in here. Well, let's do this. Today, let's just focus on 2 equations, 2 variables. Next class, we'll do 3 equations, 3 variables. That sound good? Okay. 12.1, there will be some from 12.1 that we won't talk about today. So it'll carry into next class. It's easy to identify which ones you don't need to do. You'll see. All right, so let's discuss, first of all, what is a linear equation?
It's the one that's got the variable.
Okay. Yes, I agree.
And it's just a straight line. Squared.
It's a line, right? It's a line. It's linear, right?
2 variables.
2 variables. So you'll have x and y. So something like this. X plus 2y equals 8. That is a linear equation with 2 variables in it, right? If I were to ask you to show this to me in terms of a graph, you would graph it, it would be a line. How would you graph that if I asked you to graph it?
Well, I would find y first so I can know what the slope is. And
Oh, so you'd solve for y?
yeah.
Okay, so that's one method you could solve for y, and you would get like slope, all that. So you could also let y be 0 and get your x-intercept, let x be 0 and get your y-intercept. So there are two ways to graph a line. Has this been too long? Let me do first way.
I know this is so simple, but
Solve for y. This is one method. Divide by 2 on both sides. That look familiar? The y-intercept of this line is?
X plus negative 1 over 2x plus 4.
What's the y-intercept of this line? 4, this number. I know that that point lives on my line. And then to get to another point, rise over run. So negative 1 over 2 means from that point I will go down 1, right 2. And then once I have 2 points, that defines a line, right? Agreed? All the points on this line represent solutions to this equation. And we know that there's an infinite number of them, right? For example, if I plug in 0 for x and 4 for y, wouldn't that be true? Yes? 0 for x, 4 for y, that's that point right there. But all the points on this line are solutions. Right?
So that is all the possible solutions.
That's all the possible solutions to that equation. There's a way to visualize all the solutions.
That's cool.
So what I'd like to do now
But
is
there's no individual solution that's created.
it's not unique.
Yeah.
That's right. So this is not what we're talking about today, all right? We are not talking about a single linear equation and how to graph a line. That's not what today is about. We want to talk about a system of linear equations, which means we have more than one of these. And so the way we would write that is something like this.
that was
You all right?
Yeah. Sorry.
You all right? Okay, so that's the equation we just had, right? And then I'm going to have another equation I'm going to make up here. Hold on, let me think through this. There's a different line, right? So we already know that there's an infinite number of solutions for this one, right? And if I look at that one separately, there's an infinite number of solutions for that one. But by putting a brace out here and putting these both together like this, I'm asking you, is there an x and a y that works for both of these at the same time?
So there will always be one unless they're parallel.
That's right, geometrically. Well, if they're on top of each other, there's an infinite number of answers, but
Unless they're parallel or the same.
yeah.
True.
So if I go through this and I try and, let's graph this one, okay? I'm going to just write it down over here. This was 2x minus y equals 2. And I just need to solve for y, right? So I'll move the y to the right side. 2x minus 2 is y. So I move the y to the right. I move this 2 to the left. Where does this hit the y-axis? At negative 2. And what is the slope? 2, which is 2 over 1, right? So up 2, right 1, up 2, right 1, like that. And then I can connect those together. So there are an infinite number of answers for this second equation. We are interested in finding the answer that works for both. Yes?
Couldn't you just sub the y equals 2x minus 2 for the y in the top equation?
Yes. So we need to talk about what are our methods for doing this. But I wanted you to see first geometrically, what is it that we're actually looking at? We're trying to figure out where they hit each other, right? Because the point that they hit each other, that point is a point that satisfies both lines at the same time. It lies on both lines. So it satisfies both equations simultaneously, right? So there are usually two standard methods to get this answer, right? So We are looking for this. What is that? The two methods we have names. Right, so are there any questions on the geometry of what we're looking for? Okay. To solve a system of linear equations, two variables, two equations, which is what we have, we can use one, substitution, or two, what's called elimination. There are two methods, and you're going to learn both of them. Now, substitution is usually the preferred technique when you have two equations and two variables, because it's pretty fast. But elimination is more powerful, especially when we get to next class where you have three equations and three variables. Then substitution isn't as good. So let's talk about substitution first. Since this system of equations only has two variables, I can always take one of the equations and solve for one of the variables, plug that into the other equation, substitute it into the other equation, and be able to isolate or solve for the other variable. So let me just go through it, show you how it works. So substitution first. And let's do it by just working this problem. At this stage, what you do is you look at both equations and you say, all right, I'm going to try and solve either this equation or this equation, my choice, for x or for y, my choice. So which of these equations would you like to solve and for which variable? First equation or second equation?
Second equation for y.
Second equation for y, first equation for, it doesn't matter, right?
First equation for y.
So if I were looking at this, if I were trying to solve for a variable, in the first equation, I would solve for x. And here's why. I just move the negative, or I move the 2y over and I'm done. Right? If I solve for y up here, I have to move the x over and then divide by 2, and then I create some fractions, and I don't want to mess with fractions. If I'm going to mess with the second equation, I think I'd like to solve for y, because I can just move this y over, move the 2 over, and I'd be done. So what do y'all want? First equation for x, second equation for y.
Sounds good. Second equation for y.
Second for y. That's what we're going to go for. Second for y. So I'm going to take the second equation, solve for y. Right? I'm going to go ahead and box this. That's the second equation solved for y. Now, write down your first equation and substitute, thus the name, substitution. Substitute that y for this expression.
That's kind of like that f of g thing.
A little bit, yeah. You're plugging that one into the other, except these aren't functions. So, but yeah, it is purely plugging one into the other one. So this equation becomes x plus 2, and then y is 2x minus 2, and then equals 8. Is that correct for me to write it that way? I have to have this in parentheses, right? Because that 2 distributes to the y, so it distributes to both of the terms. And then distribute the 2. Oh, notice at this stage, how many variables are in that equation? Just one. And so this is just a linear equation, isn't it? Yeah, this is just solve for x, right? Just get x by itself on one side. So I get, what, 5x? 5x here. Move this over. Equals 12. So x is 12 over 5. And that doesn't reduce. I'm just going to leave it like this. And I'm going to box it. X is 12 over 5. So far, I know half the answer.
And the y.
So now I want to know what y is, right? I know what x is, but I have an equation that I boxed earlier that tells me what y is. It's always 2 times x minus 2. So going back to this one, write down 2x minus 2 is y. We get 2 times x, but x is 12 over 5 minus 2 equals y. Multiply the 2 through. You do the 2 on top, right? 24 over 5 minus 2 equals y. And then to put those two together, you get a common denominator. So look at this as like a 2 over 1. 10 over 1, so 24 over 5 minus 10 over 5. And so you get what, 14 over 5 is y. That's it, right? Questions? We have x, we have y. Now, in terms of an answer that would look like more of a geometric solution, we would write it like an ordered pair, like a point. So if I were to go graph this point, so I'd need some decimals if I did that, right? Like 12 divided by 5 is like 2.4. 2.4, and then 14 divided by 5 is like 2.8. And I don't like arithmetic, though. That drives me crazy. All right, so this is it? Okay? So when I graph it, that's where they would hit each other. All right. That's substitution. Make sense? Let's do another one. Make this one a little bit more challenging. I'm going to put something in this one that you love, that you enjoy. I know you enjoy these. I've heard you say you really like these. Fractions.
I can smell the sarcasm going on.
What? I don't do those things.
At least I hope that's sarcasm. Just kidding.
You sure that's not your flush that you do for everybody else one?
Okay, how about this one? 1/3 x minus 3 halves y equals -5. 3/4 x plus 1/3 y equals 11.
Are these like inverses of each other, or are they just like the same thing?
How do you mean?
Like these two equations, I guess they're two different lines you just.
They're two different llines. I'm wondering if they hit each other.
Oh.
That's what's happening here. And if they hit each other, I want to know where. So we're going to use, we'll use substitution because it's the only thing I've talked about, right? So I have to choose if I'm going to solve for x or if I'm going to solve for y. And I think when I look at that, I agree that they all equally suck, right, to solve for them. But more importantly, they all have fractions, which we don't like to work with. Well, right? Is it safe for me to assume most of you don't like working with fractions? But these are equations, aren't they? So I'm always allowed to look at an equation. I can always multiply both sides of an equation by anything I want, as long as it's not 0. So the first thing I'm going to do is clear the fractions. So I'm going to rewrite this first equation. I'm going to multiply this, this, and this by the LCD. What's the LCD of the top equation?
14. Or not 14, 12.
6.
Yeah.
The least common denominator.
Yeah, just times those two,
It's
6, and then so times.
least common multiple of those two. So 6, right?
Yeah.
What happens if I multiply this by 6? I can't squeeze this one in. I'll just put it right here. 6 and then 6 here. So what happens if I do that?
You guys said 2x.
2x here
Minus 2y.
minus
3y.
This is 18, right? 6 and 3 is 18. Divide by 2. 9y. Equals negative 30. That's a little easier to look at. And then 12 on the bottom one. 12 here. 12 here. 12 here. What do I get there? 9x.
And then
4y equals 1.
That's 132.
132.
11 times 11 is 121.
I was very proud of my daughter last night. We were doing bedtime routine. She got the first. She's got the first perfect squares down up through 12, so she can do like 1 squared, 2 squared. She's 6.
She's gonna be like freaking.
I don't force math on her a lot, but went to bed and she's like, she goes, I know what 2 times 2 is, and I was like, what is it? 4. So then I started going through all the others. And well,
Let's just go ahead and go through all the squares.
but I offered her. She got $2. She earned $2 for being able to recite the perfect squares through 1 through 12. I was very proud of
She's gonna be
her.
like 12 doing Cal 1, Don't worry.
I won't force her to. I will encourage it. If she starts talking math, I won't stop.
Of course, especially when there's monetary value on the line.
Is this bad? Am I bribing her? Is this bad?
You won't force her, but are there like formulas like in her bedroom?
He's like, don't tell her.
Right. The little mobile she used to sit under when she was a baby had all these formulas.
Yeah. Instead of like the little animals, you have like
Yeah.
X's and-
Yep. Like exponential, like the exponent rules.
Quadratic formula.
All right, so look, here we are, right? We've got this thing, and we got the fractions taken care of, but we're going to run into a problem right away.
Well,
If-
yeah,
if-
the whole thing's a problem.
In the sense that if I go back and say, what do you want to solve for, x or y? You're kind of going to be in the same position. If I say I'm going to solve this first one for x, I'm going to immediately have to create fractions again, right?
Yeah, you're just gonna
If I solve this one for either one, it's fractions. So I don't think there's a way to easily avoid the fractions here, right? So we're just going to have to grind it away. So your choice, top equation, bottom equation, first equation, second equation, x or y.
Let's
bottom
do the
equation
bottom.
for y.
You want I'll let you choose this time. What? Bottom for
Why?
y. Why do you want to do that? No, I'm kidding. No, that's fine. It's your choice. It's your choice. As long as you do everything right, everyone's going to come up with the same answer, all right? Okay, here we go. I'm taking the second equation. I'm solving for y. So I'm going to move 9x over. So it becomes negative 9x. And then I have no choice but to divide by 4. What's 132 divided by 4? 33? 30. Yeah, 33, yes. Okay, I boxed this one. That came from the first equation. Now what? But wait, I said that came from the first equation. I apologize. That came from the second equation. So I'm going to take that y and plug it into the first equation's y. So I write down the first equation. And I'm going to replace this y with this. And it's fraction time. All right, so 2x minus 9 times parentheses, very important, right? Negative 9 over 4x plus 33 equals, finish off the equation, negative 30. Now distribute the negative 9 through the parentheses. positive 81 over 4x, right?
Negative.
And then negative
Negative 297.
297
Yeah, 297. Negative.
equals negative 30. And as bad as that looks, it at least has just x in it now.
Gotta stay positive.
How about we add the add 297 to both sides to get it out of there?
Yeah.
So we'll get 267 over here when we add 297 to both sides, because the right side was negative 30. And then you have to put these two together.
So that's 22.25.
Where's it? Yeah, I'm gonna do LCD here. This is like 2 over 1. So 4 on top and bottom is 8 over 4.
8 over 1.
So 8 over 4x plus 81 over 4x. And putting those two together, you get 89 over 4x. Right, that's what's left on the left side. 89 over 4x is the left side. And then tell me how I can get x by itself right now.
Dividing by
You
49 divided by 4.
Yeah, you could divide by the fraction, right? But I always prefer, instead of dividing by a fraction, to multiply by the reciprocal. So I'm going to multiply both sides by 4 over 89, which has the exact same effect, right? And just remember, when I multiply over here, that's a 1 up there, or underneath the 267. So the left side of that equation becomes just x, right? 1x. Right, the 89s and the 4s. And what about my right side? 267 times 4,
1068.
1068 over 89. And that might reduce.
12.
Oh, that's just 12? Oh, gosh, we got lucky.
Okay, so we just split those next one.
Okay, and then now we go back and get y. So what was the equation for y? It was like
Y equals 9, negative 9 over 4.
negative 9/4 x plus 33, right? That was the equation we had boxed earlier.
Yeah.
And I know x is 12. So y is negative 9 over 4 times 12. Oh, times 12 plus 33. This right here. Negative 27
Y equals 60.
plus 33. Okay, what's up?
Equals 6.
So 6. Y is 6.
Did you just like make this up now, or
What?
or you got this out of the book?
Oh, I got this out of the book.
Oh.
I had a feeling they would have nice answers. So if you look at this, that's our answer. X is 12, Y is 6. If you look at this, you know, again, if we plotted this point, this should be where the two lines hit each other. Any questions? Yes.
Do we have to go back and forth through both equations for like plugging in x and then plugging in y, or can we do like if I got that for x, can I go back to the equation I got it for? You know what I'm saying?
Oh, yeah, the original two?
Yeah.
Yes, you can always go back to any equation that would have had y in it, and x. It had to have y and x in it.
So we can solve like using one equation then we do that?
Once you get one of the variables solved for, you can plug that back into any of the equations that you have, as long as it has both variables in it.
Wait, that doesn't make sense. Then you could just have one equation and find out what x and y are.
You have to, okay, so listen, once you solve for one of the variables, you can plug that back into any equation as long as it has both variables in it. If you have just one equation with both variables, you'll never be able to solve for one of them. You'll never be able to get an answer. Like if I have x plus y is 6, you'll never be able to figure out what x is. See? Try and do it.
Yeah.
Move that over.
Why couldn't you just do?
You can't substitute back.
Yeah, but again, as you said earlier, you
Right.
can set them at each equal to 0 and plot those points, and then you have a whole list of all of the possible answers.
But that's all the answers, that's all the points that satisfy one equation.
Or like one line.
You're trying to figure out the point that satisfies two equations, simultaneously. All right, I have about 5 minutes. I just want to show you some weird scenarios that could happen, and I'll make these problems a lot easier to work with. Let's say we have 2x plus y equals 4. And let's say we have negative 6x minus 3y equals 18. Okay, which equation would you want to solve for?
Bottom one for
Top one for y. Easily. Top one for y.
Top one for y, I think, would be the easiest one. Top one for y? Okay, I'm going to take the top one for y. 2x plus y equals 4. Solve for y. Y is negative 2x plus 4. Once I have that, I'm going to box it. And then I'm going to go and solve, or write the other equation, the second one. Negative 6x minus 3y equals 18. And I'm going to replace the y with negative 2x plus 4. So negative 6x minus 3 times negative 2x plus 4 equals 18. Is everyone with me?
So I see what you're doing here.
So you get
The 6 cancels out.
Negative 6x plus 6x minus 12 equals 18.
X is going to cancel each other out. Where you do that?
But you're still left with x, aren't you?
Nope, no x's.
Okay.
12
Can't be possible.
That's not a rational statement, is it? That doesn't make any sense. Which means
There's no solution.
this line and this line
Never meet.
don't ever hit, which means they're parallel. So it is possible to have a system of equations that has no solution to it. Right? And in the language of the book, they call this an inconsistent system. Inconsistent. No solution. Okay? You can tell me either thing on a test. It's no solution or inconsistent. There is no point that they intersect each other because the lines are parallel. That's about all I have for today. We will pick up next class. We will do more of this. I'll show you elimination. On the what? Binder exam. Okay, so the binder, remember, the syllabus says you're supposed to be keeping a binder that has all your work in it for the whole semester. The initial idea was to check that at each test. And that was the thing the department wanted to do to try and improve success, right? But I bailed out of that because I did it last semester. It didn't make a difference. So, but I've offered it to people to keep their stuff together. So I'm going to offer that more like a bonus. Not like the day before the final, you throw all this crap into a cheapy binder. Like, you want to hold yours up right there? Right? You have all your work in that, right? Pretty much?
The one that I did,
Yeah.
yeah.
So something like that, where you have something someplace you've been keeping all your work. You bring that to the final. I'll give you a grade on that. That's fine.
Like all together.
Yeah, because there's supposed to be 2 checks. I'll just do it all as one.
Does it have
Okay.
to be a binder, or can it be like?
It can be just organized. I mean, just not like, seriously, people will come in and it'll just be like they're grabbing crap out of their backpack. Well, I don't really have a binder. And it's just a bunch of scrambled up papers. So just some organization.
So like duct tape and masking tape and all
Duct tape, whatever.
Really, that'll work?
Dude, as long as you make one.
So long as you can actually turn
Yeah.
all the